My name is K. Dinesh and my project mate Ramchandra Sharma. We both together did a research on energy management strategy for lightweight nickel metal hydride battery car racing in Suzuka Circuit. First of all, we would like to thank our external guide Dr.Wei-Chin Chang, Associate Professor from Southern Taiwan University of Science and Technology. He is the one who guided us throughout this research. And also we would like to thank our internal guide Dr.J.M.Babu. Introduction. Nowadays the world is concerned more about the environmental friendly automotives, which is good move. So the automotive industries are shifting towards the pure electric vehicles and hybrid electric vehicles. Harnessing the electric energy will greatly reduce the environmental pollution and leads to better future for the next generation. Abstract. In this project, the concept of SOC, that's called state of charge and discharge characteristics perform of batteries under ambient temperature. The temperature change during the discharge and batteries behavior post discharge of secondary batteries are studied and experimented in order to find an optimal ways of achieving maximum energy recovery for a battery powered lightweight car. This car is to be participate in a racing making 3 laps with the amount of battery reserve provided time interval after each lap on Suzuka Circuit, which has non-zero gradients and sharp corners. The battery model used in the research is NLAP AA Panasonic BK3MCCE 1900 mAh. That's in white color. It's called a NiMH battery. The other main approach is to sort out the best performing batteries for powering the brushless DC motor by analyzing the discharge curves, from which we can draw the inference about amount of charge left in the battery at each time interval. The batteries tested under different C rating will aid in selecting the optimal loading to be applied while the car is in the race circuit. Objective. So the first one, to study and develop an optimal recovery strategy for battery powered car on a Suzuka circuit with non-zero gradients and sharp corners. From the rules of the marathon, it comes to know the vehicle has to complete 3 laps of circuit with the different timings with a given amount of charge. The main challenge is to select the battery and motor which suits for the vehicle and marathon. Testing and optimizing the battery and motor, we can draw conclusion on how much voltage, power and torque is required to run the vehicle with single amount of charge. Discharging the NiMH batteries and selecting the optimal batteries. Literature. So the literature survey, here there are 4 authors. So the first author is Crystal N. Maxwell's. He did a research on modeling of automotive fuel cell operation in driving cycle, and he published in the year 2004. And the second author, Wu Gouling, he did a research on state of charge for a NiMH battery based on electromotive force method. He published in September 2008. And the third author, Kung Soon Ng. His title is Enhanced Column Counting Method for Estimating State of Charge and State of Health of Lithium-ion Batteries. He published in September 2009. And the final one, the Manoj Datta. He did a research on smoothing output power variation of isolated utility connected multiple PV system by coordinating control. He published in March 2009. Next one, major component. Here there are 2 components. One is brushless DC motor. Its specification is 48 volts. And the second one is AA NiMH battery. Here we are using 40 batteries and each battery voltage is 1.2 volts. DC motor. So this is the picture. The DC motor is connected with the rim, and here the specification of the motor, the system voltage of motor is 48 volts and the model is M0348DV. Appearance size, diameter 194 mm, length 104 mm, and the weight is 4.5 kg. The motor type is DC brushless motor, And the next one is rated output 300 watts and maximum output 18 kilowatts, and the highest efficiency it produces 91%. So rated load speed is 1265 rpm. And the next one is motor performance. The next one is motor performance. So here the BLDC motor is connected with the rotor shaft of dynamometer and is being made to run from starting time to ending time, where the motor can slow down its speed at specific time. That time considered to be the ending time. Therefore, we observe different torque, speed and efficiency. 8 amps current, the torque will be 2.648 Newton meter or 330 kg centimeter, and the speed it produces 1220 rpm, and the efficiency will be approximately 91% from the test results. So here totally we have 4 datas. So the blue indicates the speed, and the purple indicates efficiency, and the red indicates the torque in kg centimeter, and the green indicates torque in Newton meter. Coming to the batteries specification, here the name of the battery is envelope, and here totally we are using 40 batteries. The capacity of one battery is 1900 mAh. Complete capacity is 76 ah. Nominal voltage of single battery is 1.2 volts. System voltage is 48 volts, and low self discharge is 70% capacity, and cycle life is 2100 cycle, and the weight of one battery is 29.9 gram, length is 50.3 mm, and diameter is 14.2 mm. Coming to the NiMH battery properties, NiMH batteries find application in high drain devices because of their high capacity and energy density. A NiMH battery can possess 2 to 3 times the capacity of NiCd batteries of the same size, and its energy density can approach that of a lithium-ion battery. Unlike the NiCd chemistry, batteries based on NiMH chemistry are not susceptible to the memory effect that NiCads, that is called nickel cadmium, experience. Below are some of their properties of batteries based on nickel metal hydride chemistry. So specific energy is 60 to 120 watt per kg. Energy density is 140 to 300 watt per length. Specific power 250 to 1000 watt per kg. Charge and discharge efficiency 66% to 92%. Self discharge rate is 1.3 to 2.9% per month at 20 degrees Celsius, and cycle durability per life is 180 to 2000. Discharge test setup. So here the yellow one is temperature reader, and the blue wire is called the temperature sensor, which is connected to the battery. And there are two terminals. One is positive terminal and negative terminal, which is connected with positive and negative terminal of the battery to check the voltage discharge rate. So here the component required for making the battery holder for single battery are brass balls, a wooden block, L-clamp, bolt, nut, washer. The battery holder is assembled and the battery to be discharged is mounted as shown in figure 5.1. The connection are given as follow. As I said it before, is the same thing. Next we go to the battery results. So here you get the 1.25 discharge of 10 cells in series. So here are the 4 datas. First one is position of the battery. Second one is temperature at positive terminal. Third one is temperature at middle, temperature at negative terminal. So these are the temperature, these are the power. White it indicates power, blue indicates temperature, and orange indicates volts. As you see, the voltage start at 10 and it gradually downs, and again it flows a parallel, and then it finally discharge below 2. That means it took 20 to 23 minutes to discharge this 10 cells battery. So this is the graph of the 10 cells. And next one is battery results. The continuation of battery results, and this is for 1C discharge of 40 cells. So here we totally tested 80 cells and we found only 40 is the best one, and we did at 1C discharge of 40 cells. So during the test setup, the room temperature and the temperature of battery both were observed to be 29.5 degrees Celsius. Battery case temperature was read 30.2 degrees Celsius on the TS2730 multimeter display. The 4 feet K type chrome aluminum thermocouple wire TPK01, which is plugged into the T72730, aided us in measuring the temperature. The probe tip is beaded. The test is conducted under constant current loading, and the current is set to 1.9 amps. According to the norms, the discharge test should last about 60 minutes for fully charged batteries with 1C load. A cell of rated nominal voltage 1.2 volts will show 1.438 volts when fully charged. So in the pack of 40 cells in series, we observed open circuit voltage VOC is 56.80, which is assumed as 1.42 volts per cycle. With 40 cells, it's hard to pick a reasonable stopping point because possible imbalance between cells could be significantly, especially after a few charge and discharge cycles. Battery results continuation. So here the single cell for 0.5C. Here the same each batteries we did different C ratings to check which one is the best thing. So this is for 0.5C discharge of single cell. When the voltage drops to 0.9 volts, it is assumed that the state of charge in the battery is considerably low. At this level, roughly 95% of energy is spent and the voltage would drop rapidly if the discharge were to continue. It is suggested not to discharge beyond 0.8 volt to avoid damage of the battery. The battery discharge curve characteristics are observed from the graph, or exponentially discharged, and second one is battery is discharged to near rated capacity as it's shown in the graph. And after discharging the voltage, the battery is being removed. The voltage is been switched off, and the post discharge we noted that the voltage gradually increasing as it's shown in the graph. So in this post discharge result, we observe the voltage is increasing and with decreasing in temperature. When the load is removed after discharge, the voltage of the health battery gradually recovers and rises towards the nominal voltage. It took the NiMH battery about 57 minutes to get back its nominal voltage of 1.2 volts and the temperature 31.7 degrees Celsius. And the next one is 1C discharge of single cell. So according to the norms, the discharge test should last about 50 minutes for fully charged batteries with 1C load. A fully charged cell will show 1.438 volts. We observed open circuit voltage VOC 1.3489 V and power 2.20 watts. When the voltage drops 0.9 V, it is assumed that the state of charge in the battery is considerably low. It is suggested not to discharge beyond 0.8 V to avoid damage of the battery. The maximum temperature rise was observed to be 35.3 degrees Celsius. And the next one is post-discharge. From the post-discharge result, we observed the rise voltage. The nominal voltage took lesser time compared to the post-discharge test. Results of 0.5C rating. The nominal voltage rise shown the way above the nominal reading of 1.2 V. And the next one is 1.5C discharge for single cell. When the voltage drops to 0.8 V, it is assumed that the state of charge in the battery is considerably low. It is suggested not to discharge beyond 0.8 to avoid damage of the battery from the From the graph, we can infer that the discharge curve show relatively flat line for a longer period of time, but the total discharge time was shown to be lagging by 15 minutes. So the discharging at C rating is not recommended for some application. The maximum temperature rise was observed to be 38.2 degrees Celsius. In the post-discharge test of 1.5 C rating, when the load is removed after discharge test, the voltage and the temperature are observed to be back to the normal in a shorter span of time. The voltage level raised to be 1.24 volts after 27 minutes of load removal. So finally, the summary of results. As we increased the C rating, the open circuit voltage was getting decreased. The second one, from the curves of discharge test using different C ratings, discharge yielded linear degradation. The third one, the battery is discharged to near rated capacity. The cell voltage is observed to be degrading in direct proportion to the remaining capacity. The final one, from the motor graph we observed for 8 amps current, the torque will be 2.648 or to 30 kilogram. Speed is 122 rpm, 1220 rpm, and efficiency will be approximately 91% from the test results. Thank you.